Welcome, everybody. Welcome to the OR personnel. We're great to have you, and thanks for coming. I know that's it's unusual to have you here for Grand Rounds, but we're delighted to have you. It's my honor today to introduce Dr. Rob Shumsky. He's still helping set up the audio visuals, I guess, for his talk today. So I met Rob about 3 years ago when I was kind of feeling a little restless and wanted to learn a bit more about healthcare organization and management. And Rob, among his other accomplishments, currently runs the program out of Dartmouth for what's called a Master's of Healthcare Delivery Science. He has a background in applied math from Harvard, and then a Ph.D. in operations research from MIT, and he's a full professor at Dartmouth. He has conducted research on U.S. air traffic management and transportation operations for a number of state agencies and for the Federal Aviation Administration. And more relevant to our work, has worked as a consultant for manufacturing and service operations, including call centers and healthcare provider organizations. So he's here today to talk a bit about how we might optimize our clinical operations, and I think he's going to take it from here. And you already have perceived there's some sort of a participatory aspect of his lecture, and I'll let him describe that to you.
Thanks, Bob. I really appreciate your introduction and being here. First of all, thanks for your patience. I know it's not usual that you get ordered around when you come to one of these grand rounds, but I hope you'll see why we're lined up the way we are. Just to quickly give you a sense of what's going to happen. I went on the website, and when Bob asked me, I read about what are neurosurgery grand rounds, and it says that they're didactic lectures on current and emerging interventions for cranial and spinal neurosurgical conditions. And my first question is, what am I doing here? So I am not a healthcare provider. I'm not a surgeon. I know absolutely nothing about neurosurgery, so I want to get that out first. I did have the honor of teaching Dr. Hart in the program that I helped run, the Master's in Healthcare Delivery Science at Dartmouth. I taught a course called Operations Management, which is the sort of the ideas and structures and mathematics of how systems work. So my original research was in air traffic control in airports, and more lately I've been applying some of those ideas to healthcare, and in particular to hospital flow. So what you're going to see in this talk is some general ideas about flow, in particular about the impact of variability on flow, and then the impact of variability and uncertainty on the design of general healthcare systems. So the talk will not focus specifically on neurosurgery, but more on in general on how things work in healthcare. And I want this to be an interactive session. I'm terrible at just lecturing, so please, if you have questions, you have comments, stop me, ask questions, and we'll go from there. So the agenda is we're going to start off talking about the physics of systems with variability. By physics, I mean how does it work? Because of gravity, when you drop a book, it falls to the floor. It turns out that there are similar physics to how systems with variation work. And we'll start with a physical simulation. You'll see that. We'll have then a computer simulation that we've cooked up for you, and some equations and graphs that sort of help to explain how systems work. We'll talk a little bit about methods for managing variability in the presence of inevitable variability. We'll talk a little bit about economies of scale, sharing information. And finally, I'll get to something I think is incredibly important in healthcare, which is co-production. That is the involvement of patients in the healthcare delivery process. So this is fairly high-level view. The course I taught with Dr. Hart was 6 weeks. I'm going to do the whole course in hour, so I'm going to talk really fast. I want to first thank Dr. Hart for inviting me. I also want to thank Linda for her help. She's been amazing. Where is she? I think she's still out there. So, let's go. Okay, so as I said before, here's the instructions. You have a seat. Make sure there's no empty seats. That looks good. Have something to write with, please. So if you don't have a pen or pencil, maybe borrow something from someone next to you. There is a blank index card in front of you. Don't write on the card yet. And when I say go, here's what we're going to do. Each of you will add value to the cards by drawing smiley faces, okay? So instead, we're going to be creating happy patients, I guess we'll call it, okay? And that's when I say go, but not yet. And to start, all of you are going to draw 6 smiley faces on your card, all right? And once you draw on the 6, you'll pass it to the next person. I'll have specific instructions right now. So here we go. Making happy patients continue. When I say go, not yet, you'll draw 6 smiley faces. You'll pass the card to the person on your left. If you're on the end, you can place the card on the ground. If you are on the right over here, there is a pile of index cards that are ready for you to keep going. So we're basically creating a simple production line using using these cards. Here, I'm going to get my timer out because I want to see how you guys do. By the way, this is the first time I've ever tried this experiment, so I hope it works. We'll see. Okay, so we're going to repeat, and so basically just keep those cards going. Keep those smiley faces going. Now, if the person on your left is busy, then just place a card between you and keep drawing. Now, this is a very high quality production process. We're going to have Press Ganey is going to be asking the cards afterwards how well you guys did. So try to keep the smiley faces looking good. Let's see, draw anywhere if the card is filled up, even over other faces. And the goal of your row is to complete as many cards as possible in the time period. I'm going to probably time about 2 minutes. Before we start then, any questions, you guys? Any questions about how this works? Yes, there are 2 sides. Use the blank side. If we run out of cards, I might end up turning them over and reusing them, but for now, use the blank side. Good question. Thank you. Your name is? Ben. Ben, nice Ben. Thanks. Other questions? All right, in the back, we're going to use, it's a little more complicated. I like you guys, this is one long production line here. Okay, so if you get to, someone already started. I see 6. That is that's not good. That patient wasn't even disinfected yet. That's not good. All right, so that's, okay, so we want to you press it over here, and then this group here will be a single production line. If you want to kind of go like in an S shape, that would be great. And I'll try to get more cards for you all here. We have quite a turnout. I'm so excited. Yay. Here we go. I'm going to steal cards from you guys. Here we go. So you guys will start here. All right. Any more questions?
Bob, I have one question.
Yes, Bob.
So as they receive the card with 6 smiley faces, they're to draw further one more?
Well, one more group of 6. So in the end, for example, this row has 10 surgeons on it. You will have 60 smiley faces in the end on the card. Great question. Other questions? Ready, set, go. Beautiful. Oh my goodness. This is a happy patient. That is great. So you'll put yours right here. This is really interesting. Sorry, your name again?
Oh, Rod.
Rod?
Yeah.
Rod, okay. Thanks, Rod. ROD, okay. Can remember when you're done, put it on the floor over there. Okay. Okay, minute and a half gone by. Okay. So Bob, when we're done, when I say stop, if you want to count how many cards are. And four, if you also want to count the number in front of Rod, so that would be nice. Okay, I'm going to count down to 10. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Stop. All right. All right, everybody. Wow, beautiful. This is a wonderful hospital. You have successfully completed large numbers. Bob here is going to actually do some counts, and we're going to take some performance measures here. Here's some results. Okay, so Bob is right now counting what we call the throughput. That is how many patients you all produced in the time we allotted, which was about a little over 2 minutes. It was about 2.25 minutes. So Bob's getting an average, but there's actually 3 interesting performance measures to look at here. One is called WIP, which is the number of cards in process. We are going to count, for example, for this table, 1, 2, 3, 4, 5, 6, 7, 8, 9. So really only 1 per person. So there's about 9 or 10 in process here. I see 9 or 10. There's a few extra over there, maybe about 11 in process. Looks like sort of 1 per person. So the WIP right now, on average for each row, is around, we'll round it up, around 11, say, 10 or 11, because 1 per person. I didn't do much timing of how long it took a card to get down the row, but I'm going to estimate, from what I saw, it was sort of boom, 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 boom. What do you think? About 1,000, 2, 1,000, 3, 1,000. I'd say about 25 seconds. You guys were working at the rate of about 2 seconds per smiley face, so maybe around a half a minute to get down the row, and I'll take some timing later. So about half a minute. Bob, around, it can be round numbers. How many did we get for throughput?
So average over about 5 rows, and giving Dr. Shumsky the benefit of the doubt, having half to do the single card.
we'll get back to row 1 in a second. Yeah. Yeah.
So we're right around 10 to 11-ish average.
Okay, great. So around 11 cards. Let's do 11 cards in 2 minutes. Okay, so around 11 cards in 2 minutes. Sorry about my writing. And finally, quality. What do you think? What do you think, Bob? What's the quality of the
Variable.
Variable? I see. And so the quality, from what I saw, it was pretty good. They look happy. Now Rod here is an interesting case. He decided to really, and we're going to talk about Rod in a few minutes. Actually, you're a special case. But other than that, it looks pretty good here. So quality, I'd say, is pretty good. That's the first set of experiments. So we're going to change things up a little bit. Where before each of you drew exactly 6 smiley faces. I'm going to change one thing in this experiment, and we're going to run it again. I'd like you each to draw exactly the same number of smiley faces as your birthday. Okay, so if you were born in January, you're going to draw 1 smiley face. If you're born in February, 2 smiley faces. March, 3, April, 4, all the way up to December. Guess how many smiley faces? They'll draw 12, okay? So I'll point out that the average number of smiley faces that you all will draw is still approximately 6, a little over 6. But instead, we're going to have each of you draw a slightly different number. So let's take a look. Here we go. So there it is. That's the new instructions. So once again, when I say go, you're going to do exactly the same thing, and you can.
Where's the card? Are we drawing on the same card?
Yes. So you can, to keep things even and fair, you're going to start up and draw on the existing card. So just add to the card in front of you. And I'm sorry.
send them right?
Nope, exact same production line, exact same instructions. The only difference is that the number of faces you draw will depend on your birthday. Everything else is exactly the same. Is that okay, Zoltan?
Yeah, but where's the card?
Where's the card? Oh, there is no card in front of you. We will, if you're missing a card, let's distribute cards so you all can get ready. Good. Anyone else need a card to start up?
Thank you.
There we go. You're welcome. Thanks,
Dr.
Zoltan.
Skewy does.
All right, good. There you go.
Thank you.
You're welcome.
One right here, Rob.
There we go. All right. So, any other questions? We need more cards. Great. There we go. There we go. And you guys are out of feeder cards. All right. So let's see. I'll make sure you guys have enough. Thank you. All right. Ready, set, go. All right, let's keep that line going, guys. Come on. Here we go. Yeah. Thanks, Linda. Thanks. I think there's a problem with incentives. People aren't working hard enough. I see idle people. People just sitting there. What's your name? I'm sorry?
Irina.
Irina. Irina. You're not working. Come on. What's going on? Mary, oh, geez.
Careful.
Okay, all right. All right, come on. Let's go. Oh, batching. Excellent. That's great. All right. Let's see. And Bob, at the end, we'll have the same count. Thank you. Cards. Here's some more cards, guys. There we go. Okay. Let's go. Come on, everybody. All right. 10, 9, 8, 7. Get that last card done. 6, 5, 4, 3, 2, 1. All right, stop. All right, thanks everybody. Wow, you guys work hard. All right, let's do a quick count now. We're gonna do a similar count for different this different process. So in this new process, we have people drawing their birth month instead of just 6. So let's first talk about the WIP, the number of cards in process. I'll do a quick count here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, you know what? With Rod, I'm not even going to bother. Okay, so here we go. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 in this row. If this row could count how much WIP you guys have, how many cards are in process, all right? So just get together and count that. We have here 1, 2, 3, 4. You guys have 1, 2, 3, 4. Oh, wow, how many's in that pile? Uh-huh. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20 in this row. We had 20 WIP there. This third row, what's your approximate WIP? 13. You guys have WIP of probably, it looks like around 15, I'm guessing, because I see a few extra there. So I think average WIP went up. Slightly. I'm going to guess the average whip is around, with the 20 back there, around maybe 17 or so. Just a round number. Bob, what was the throughput?
It's about 8-ish.
Eight cards. Yep, 8 cards in 2 minutes. The average lead time from a card, I estimated, went up to about 45 seconds from about 30 seconds. And quality is still pretty good. So what do we see here? I want to emphasize the average number of faces that were drawn on the cards remained approximately 6. But all the performance measures we have here declined somewhat. So we had about, looks like about a 30% decline in productivity for the row, with an increase in WIP. And WIP is a good measure sometimes of financial success. WIP is money. It's money invested in the system that isn't being used, so that went up. The performance measure of lead time, which is incredibly important in healthcare, how long it takes to get through a system, went up as well. And you guys maintain quality pretty much, as you said. So quick, give me an explanation. Why did things get worse? What was the big difference between the first experiment and the second experiment? What happened? Yes?
They're bottlenecks in the system.
They're bottlenecks.
Like for us, I think we had like 10, 5, and 8. So we predicted early on that there was going to be a bottleneck right here.
Right. So this you were born in
October.
October. Okay, so in
I'm not
October.
gonna hire people born in the end of the year.
No, yeah. So we're gonna
All Januaries, right?
we're gonna tighten our recruiting here to look for early month births. That's a really good point. So October's our bottlenecks, and bottleneck is a resource in the system with a production rate that's slower than the resources around it. It's not able to get as much through as fast. Okay, so yes, Ron.
Actually, so I like doing the second round because I felt less pressure.
Rod, you felt less pressure. Yeah.
So
yeah.
I didn't necessarily, I sort of, in the beginning you were kind of stressed. What does it look like? What are they supposed to be?
Yeah.
And then the second one, I just kind of was more creative.
Yeah. You can see this with Rod. This is Rod. What month were you born in?
June 6th.
You're June, so you're kind of in the middle. It's interesting. Now, Zoltan, what month were you born in?
September.
September. Okay, so it's interesting that you felt less stressed because actually Zoltan comparatively is a bottleneck between you two. So if you have a bottleneck in front of you, things feel less stressed. But let's find someone who was a bottleneck. I know back here, I think we had a bottleneck. Your name is
Mary.
Mary, and what month?
November.
November. How did you feel during that exercise?
Pissed.
You were pissed, okay? You were
I know, my parents.
Mary was not happy, and bottlenecks always feel pissed. They always feel like they are, and because ultimately there's a famous saying that the productivity of a system is determined by its bottlenecks. Okay, so you are the focus. You are the thing in the system that's determining its ability to produce, and as you saw before in the first system, which was incredibly balanced. So it's called the balanced system. There were no outstanding bottlenecks. Everyone was working at exactly the same pace. And when you're designing manufacturing lines, that's sort of the holy grail. It's very hard to get that to happen. But in most systems where there is variability, that is, there's variability in the amount of work to be done between resources, you're going to have the appearance of bottlenecks in some places and not in other places. So that's the crucial difference between these two systems, and that variability will result in decreased performance across virtually all measures. And in most cases, this goes down too, because people get upset, they get pissed, they get worried about what they're doing, and you get worse outcomes. All right, so that was happy part 2. Here we go. Okay, so ultimately the problem in the second system were these temporary or permanent imbalances between demand, say from Januaries. Januaries are spitting out cards at a fast rate, and supply from Decembers. The supply of work from Decembers was lower than that from Januaries, and you see those imbalances overall. Underneath that is just the simple fact that there's variability in the processing rates between the various resources. All right, and just as an example from an ED, suppose Patients arrive to an ED at the rate of 9 per hour, on average 1 every 6.7 minutes, all right? So pretty slow. It's probably like Dartmouth. It's not a very busy ED, once every 6 and a little minutes. The ED has a capacity of 10 per hour. So they can handle an average of 6 arrival 1 every 6 per minute. So arrivals are 9 per hour. Capacity, that is, they have triage nurses and doctors that can handle a rate of 10 per hour. In other words, you have arrivals every 7 minutes or so, and you can deal with them in 6 minutes. So what's going to happen in an ED that's built like this? What do you think will happen? What will it look like in the ED? You've got capacity higher than demand. Good? Who says good? This is a well-designed ED. Things are going to go well. Who says not so good? Who says absolutely nothing because it's way too early? And OK, that's you. OK, but that's OK. To me, this looks good. They've got what's called a capacity buffer. It's extra capacity to deal with things. All right, so let's take a look. We're going to have, this is a simulation that I know Bob had fun playing with when we did this in the class, but we're just going to take a look at what happens. It's called a queuing simulation. And when I start, this is sort of time sped up. You can see people arriving to the ED, and there's the triage nurse, and we're doing well, all right? This is great. Everyone's getting in. They arrive at an arrival rate of 9. There's a service rate of 10. No one's waiting. What's missing from this simulation? What? Variability, OK? This is your perfect production line with no variability. In practice, do people arrive exactly every 6.7 minutes in an ED? No, why? What happens? Why do people come faster or slower? Give me some ideas. Why does it happen? Natural disaster, OK? A car accident. You get clumping. Maybe 2 kids in a family are both feeling sick. Just by chance. It's like if you put a Geiger counter to radiation, you hear clicks. By chance, what happens is people clump or spread out over time. So what I'm going to do is I'm going to keep the arrival rate exactly the same, but I'm going to increase the variability of the arrivals. All right? This is called the CV. It's the coefficient of variation. And it's keeping the exact same average, just like the 6 smiley faces, but now people are tending to clump up. So what we're graphing here is the waiting time, how long people waited to get in to see the nurse. And you can see, even though the averages are exactly the same, now we're getting 24 minutes of waiting, 36 minutes of waiting. It's going to go up and down. The fascinating thing is that because the arrival rate is 9 per hour and the service rate is 10 per hour, over the long run, this system will have 10% idleness. That is, 10% of the time, there will be nothing happening. So if you look at this x-axis, 10% of the time you will be down here. But the other 90% of the time, you're going to get this fluctuation, this variation. So even with what's called the capacity buffer, in the presence of variation, you get this kind of variability. In fact, we only have half the variability that could exist in the system. Not only could you have arrival variability, but you can also have service rate variability, the time it takes to handle a patient. Now, you all are very familiar with service rate variability in your OR. How long a surgery takes, and you've got your schedule, and you've got your actual, is highly variable. What's the minimum in neurosurgery? What's the kind of fastest you're going to ever get a surgical suite starting to ending a particular case? What's the minimum time? An hour. So an hour is probably the fastest you've got. What's the longest case you've ever done? Who's done a case? We were talking about this last night. 15 hours? 14 hours, OK. That's highly variable. So I'm going to add service time variability to the mix here. Right now, everyone is taking exactly 6 minutes. We're going to bump it up a little bit. Here's service time variability. And now you'll see things are going to get even worse. Because this is a random simulation, it might take a while to see it. But in fact, what I'm going to do is I'm going to pause and speed up things. Here we go. Let's put the simulation speed up here, and here we go. All right, let's see what happens with both arrival and oh, look at that. That's not good. An hour and 48 minutes. Oh, 2-hour waits. That's right. And again, the fascinating thing is it will come down. This is a system that's only 90% utilized. I predict, I hope, at some point it will come down and you'll get that idle period as well. But right now, things look grim. Oh my goodness. All right, this is a 2.5-hour wait in ED. ED used to get up to, as you know, 5-hour wait, 6-hour wait sometimes, but this one is not doing well. Should I wait? Okay, at some point it'll come down. Any questions so far? Thoughts, questions, concerns? Am I missing something in describing? Here we go. Oh, I'll get down. Okay, and we have drained the system right. Nope. All right. Well, let's go on. There it goes. Okay, fine. Whew, all right. And again, 10% of the time you're going to be down there, and then it'll pop up again. All right. So you could watch this forever. It's very mesmerizing to me. Let's pause it. All right. Let's go back to the system. It's like SimCity, exactly. So here we go. All will be well, not necessarily, certainly not in the presence of variability. All right, so where do you see variability? So certainly you see it in healthcare. You see variability in the arrival rates of people over time. This is a graph of arrival rates to an ED by acuity level. You see dips in the morning. You see bumps up around midday, and then it goes down again. So you get this variation in time. Ooh, I did it again. This is, okay. There we go. I will avoid that spot, definitely, okay? So, and the thing about this variability is that there's not only this predictable variability during the time of day, but there's also, as we saw before, very random variability, unpredictable variability that happens around that average, and that adds to the queuing behavior as well. This is demand variability at Atlanta's Hartsfield Airport, okay? So you can see this is the number of planes that are rolling out to the runway at any particular time. Who's ever flown out of Atlanta? Do you remember being in like what I call a plane queue on the tarmac and on the rolling out to the runway? What's happening here? Why do you see these spikes in variability? Can anyone explain why you see this sort of crazy variability? Rushes of planes, then it's quiet. Rushes of planes, then it's quiet. What is Hartsfield? Who flies in and out of Hartsfield mostly? Delta. It's a Delta hub, okay? So a hub airport is one where they have lots of people making connections. In order to make the connecting flights reasonable in terms of duration, what they often do is they schedule banks of flights all together. People get out, come to a new plane, and everyone flies out at the same time. So this is incredible variability that's baked into the system. They're doing it on purpose in order to minimize the connecting time between passengers. But the result is that you need enormous amounts of resources at the airport to handle these spikes in variability. So as an example, if I'm scheduling my luggage loaders and my gate agents, you end up having to schedule for the peak rather than the average. And the peaks are way higher than the average amount. Every resource at Atlanta has to be scheduled around the peak demand for one of these banks. They're called banks of flights. You have to schedule luggage loaders for them. You need to schedule gate agents. You need to schedule ticket agents. You need to build in those terminals. All of them have to be scheduled for the peak. And that's what the variability does to you. Another culprit, as we saw, is service time variability. This is a classic example in healthcare of service time variability. Service time in this case is length of stay in an ICU. You see that the average length of stay is about 4.2 days right here, but the variability around that average is enormous, all the way here up to about a month. That is the service time variability. The time it takes to get someone through the system is variable. I see the same sort of variability in airlines. I did a project with Homeland Security, actually, looking at how long it takes to go into the belly of a plane and grab a bag. If there's a concern about what's in the bag, this happens sometimes. You might be waiting. You'll see someone coming in. The time it takes to find the bag in the belly of a large aircraft is highly variable. And that variability has its sort of influence on the entire system. So you see that. Now things can get worse than what we saw before. In the version I showed you just a minute ago, we had what was called a 90% utilization. That is, the ratio of the arrival rate over the service rate was 90%. In practice, some crazy people schedule the arrivals to be very close to the service rate, thinking that they're going to save some money by reducing capacity to be fairly close to demand, and that's always a very bad idea in the presence of variability. Again, this is a stable system. 1% of the time, things are going to be down here, but as you're going to see in a second, I'm hoping it is random, chances of things getting very bad is very, very, very high. And you'll see, the problem with randomness is that you never know what's going to happen. This looks fine, no problem at 99% utilization, but pretty soon you'll see just by randomness things getting up and up and up and up and up. Okay, so now in general we actually have mathematical. There we go. Bye. All right, that is sad. Okay, so we'll pause this and we will go back to the slides. So we're in the realm of what's called queuing theory. This is queuing theory. This is a classic formula called the PK formula, or the Pola-Chekhinchen formula, and it allows you to predict how long the wait times are going to be for patients that are coming into a system like this. Don't worry about the math. The key part of this formula is this thing right here, the 1 minus rho, and 1 minus rho, and this is utilization. This is the ratio of demand to supply, this thing right here. And as you can see, as that goes towards 1, remember your high school math, what happens to the fraction? If the denominator goes if the rho goes towards 1, the denominator goes towards 0, and the whole fraction goes to infinity. So this basically will blow up on you, and that's what happens in any real system. There's lots of equations. You don't want to deal with this, but the basic message is very simple, and that is, as utilization goes to 100%, queuing systems blow up. Things get very, very bad very, very quickly. Now, in a real system, there's usually a safety valve. People just leave, or you cancel the surgeries, or you put in overtime, or you do other things. But in general, you've got to, in a system with variability, you've got to avoid 100% utilization. So the next time how many here are managers, heads of, don't schedule at 100% utilization, okay? You think you're saving money, but what you're going to get is bad results, okay? So the other thing is to remember that this is all caused by variability. The CAs and CSs here are measures of variability. They're called coefficients of variation. And what I'm saying here is that as you change the variability, you can move this curve. So if things get worse in terms of variability, then at a given utilization, you're going to have a higher wait time or a higher amount of congestion in the system. And this just goes up and up and up. So at 100%, it's really, really high. But the good news here is that if you reduce variability, you have a much more stable system over a much wider range of utilization. And things get very calm. So the next time those irritating people who do Six Sigma or Lean or things like that start talking to you about reducing variation and reducing variability, this is what they're talking about. One of the reasons why they're so into it. Because in a system that's very predictable and not as variable, you get a much more stable system over a wider range of utilization. Okay, and that's why all these quality improvement methods are focused so much on variation in their systems. So that's one thing. Any questions so far? Again, we've done the first 2 weeks of my class in 40 minutes. How are we doing? All right, keep going with me. You're going to do it. Okay, so what do we do? How do we manage under variability? So certainly one way is to reduce utilization, to not have as much work coming into the system as you have capacity to handle the work. All right, so but that can be expensive. It can be expensive either because you're reducing revenue by reducing the number of, say, surgeries you're scheduling, or you're increasing the number of surgeons, surgical suites, things like that. That can be expensive. So you can increase capacity or reduce demand. Often those aren't favored ideas. You can try to reduce variability. That's what I'm obsessed about. That's what I love. You can make a much better system by reducing variability, but variability sometimes is inevitable. All patients are different. Again, last night we were talking about neurosurgery in particular. You guys have probably, in all the healthcare space, the most variability in the types of patients you're dealing with, the time it takes for surgery. So at some point, there's nothing you can do about it. So what else can you do? What other ideas are there for managing under variability? Okay, so here's one idea, which is very common out there. And I'm going to ask you to compare two systems, all right? Very simple systems. These are two systems. Whoops, sorry. Two systems that went away. There it is. System A, you have two separate queues lining up for two separate servers. This is a check-in desk for, say, a primary care physician. In System A, you get to see, let's get some names here. Your name is?
Meg.
Meg and? Josh. Josh, okay, so we have Meg and Josh. This is Meg. And this is Josh, and it's a very personalized system. If you enter the system, you commit yourself to either Meg or Josh. Every time you come to the system, you like to see Meg or Josh, and you line up for Meg or Josh, and you will not go to the other one. All right, so there's a hard boundary between these two systems. In System B, so that's like if you went into Starbucks and you have a favorite barista. That barista's kind of cute. You always want to see the same one. That's the one you always get. All right. In System B, Meg and Josh are still there, and they still do the exact same amount of work. But as you line up, you end up with seeing either Meg or Josh if either is available. Okay, so in terms of effectiveness and efficiency, I'm going to ask you to vote for System A or System B. Which one is going to sort of operate better in the long run? Who votes for System A? System A operating better. Who votes for System B? Oh my gosh, all right, you guys get 100%. Yeah, System B has what's called economy of scale. By having a pooling between those two servers, you automatically get some efficiency because in particular, if Meg is not waiting for anyone, but Josh is completely overloaded in System A, Meg is idle and can't help out. In System B, Meg can help Josh and Josh can help Meg, and you don't have as much idleness or idle time. Okay, so this is called economies of scale through pooling, and it's a very, very powerful effect over time. If I take two separate systems that are small and combine them into a single system, and what I'm doing in this graph is simply changing the number of servers and proportionally raising the arrival rate to simulate what happens with pooling of systems, you see very dramatic effects going from 1 to 2, 2 to 3, 3 to 4. So two separate hospitals with two separate neurosurgery units with two separate sets of surgical suites, if they're small, by combining them and letting them help each other out, you're going to get much better effectiveness in terms of waiting time. But you can see that economies of scale decline. The effect of it is reduced as you go higher and higher. So I do some work with call centers, for example, and when I hear that you literally have a 200-person call center over here combining with a 400-person call center over here, there's no economy of scale. You already have all the economy of scale you're going to get with 200. Going up to 600 makes very, very little difference. But when you're combining two small systems, the effect can be enormous. All right? So then when hospitals merge, they often make an economy of scale argument. It's true if you're combining small units. It's much less true if you're combining large units. All right, just another economy of scale example. Next time you order from McDonald's, it's probable that when you're talking to the person here, that person is the person right a few feet ahead of you who's going to fill the order. But there are groups of McDonald's where you're actually talking to someone in Dayton, Ohio. They've decided to pool the order taking process and then send that order back to the local McDonald's because it allows you to pool that particular work. It actually used to go to Indonesia. That was kind of funny that they would actually take the order in Indonesia and then send the order back, but they actually moved the call center to be a domestic call center. So you'll see that happening as well. There's lots of examples. There are some hospitals now who, for example, pool patient calls. It might be pooled at a call center, might be pulled across various wards, but it's a way of trying to get economy of scale. All right, so there's quickly, now we're up to the third week of the course. You guys are hanging on. All right, so there's one idea for managing under variability. Another idea for managing under variability is supplying information. Okay, so this goes to some research that I'm working on right now, actually, which has to do with what information do you give patients as they begin waiting? So let's assume in an experiment, and we've actually run this experiment at an ED in Chicago, that we've implemented a sophisticated wait time forecasting algorithm in an ED. It's a big data thing. It's got fancy data mining and AI stuff in it. And basically what it does for each patient, it produces a very specific forecast. The forecast for the wait time depends on that patient's level of severity, its severity index for the patient. It depends on the time of day, the current queue, the number of doctors, what they're doing back in the back, and all of that time is put into a forecast. And the problem with forecasts is that there's no perfect forecast. And it turns out the median of the forecast is 1 hour, but based on the historical data we have, there's a lot of variation around that forecast. We're not really sure exactly how long it's going to take. In fact, the 70th percentile for the forecast of the patient waiting time is 2 hours. Again, this is an individual forecast for that patient. The 90th percentile is 3.5 hours. So it's really not, we're not certain of the wait time. We just know that the median is 1 hour, okay? So the question now is, what do you tell the patient? They've arrived. You've got on PC, on your computer readout over here, this forecast of waiting time. This is caused by variability in the system. It's inevitable. We can't, unfortunately, get a single spike at 1 hour and guarantee it. There's going to be variation. What do you tell the patient? All right, here's 4 options. Option 1, I'm afraid you're going to be waiting, but you don't tell them anything in particular, all right? So just general vagueness. You tell the median time. It'll take an hour. Tell the patient to expect a longer waiting time. Think according to our individual AI-based big data mining forecast, it's going to take 2 hours. Oh, it's going to take 3.5 hours, all right? So there's four different options, all right? Vote for the one that you believe patients prefer to hear in the long run. Which one is going to maximize your Press-Ganey score out of this ED in the long run, okay? Who votes for don't tell them anything? Who votes for tell them the median? This is sort of the most, in some ways, the most honest one, right in the middle. This is what we expect it to take. Who votes for take 2 hours? It's going to take 2 hours. And who votes for takes 3.5 hours? All right, interesting. You guys are sociologists, because we could have saved ourselves some time. We actually ran the experiment with 4 treatment groups and then asked later, how satisfied were you with the wait? And we actually validated the results with the Press-Ganey scores that they gave later on. And here's what it looks like, okay? So the y-axis here, it is not, we didn't have a lot of variation. It was statistically significant, but it's not a huge, although changing Press-Ganey scores is really hard, actually. So with no announcement, you're right, not very good. 50 percentile, people want to know how long they're going to wait. So that's a slight increase in satisfaction. The 70th percentile, as you guys anticipated, was the best. The 90th percentile was a little less, but actually still better than these two. All right? And what's going on here? Underlying it is the idea that when you're supplying information, it is best, this is sort of an old saw, it's best to underpromise and overdeliver, but don't freak them out with really bad news, okay? So that first initial forecast is, say, of 3.5 hours. If they then get in after an hour, of course they're pleased. But they've then spent a full hour sitting there stewing, worrying about the 3.5 hours. And that's affecting their psychology. That's affecting their rating. So we're actually now doing some experiments. And all of this is based on Kahneman and Tversky's prospect theory, the idea that we are loss averse. And getting bad news is a form of a loss. If you hear bad news, you're adjusting your expectations from something you think was good to something you think was bad. On the other hand, getting in before you thought you would is a gain. And balancing those losses and gains is what kind of we're examining. And we're actually coming up with optimal delay information releases. This example, for example, only had a single announcement at the beginning. How do you update that announcement as time goes on? What's the best way to do it? What's the best way to kind of trickle out that information is kind of an interesting experiment that we're doing. Okay, so there's another way to manage variability, and that is managing variability through strategic information revelation, and that's what we're working on here. All right, so I'm going to move to one more topic, and then maybe we can have some conversation and some questions, and that is the question of co-production of services, because healthcare is different from most call centers. It's very different from the airline industry in that the patient involvement is often crucial for successfully producing what you want to produce. So in all industries, we see a variety of types of co-productions, okay? You see what I call provider-led interactions. That is someone with a particular expertise who then provides the service with perhaps a little input from the customer, but not a whole lot. I think expert barber is someone who is sort of provider-led. There's self-service, in which the firm sets up the environment in which it will a customer or a patient can thrive, but then the patient does most of the work. So a salad bar is like that. And then there's true collaboration between the provider and the patient. In this case, sort of a discussion, maybe a discussion about what to do. So one underlying question we have, and I know a lot of you have to go soon, and please, leave if you need to, is why is there a variety of methods of collaboration here? And of course, the answer again is variability. There's underlying variability in things like the ability and willingness of people to participate in the co-production process, and there's variability in the needs of diversity among the customers. And if you take these two types of variability into account, you can end up with a variety of structures for co-production, either full self-service or true collaboration. And we've been working on finding ways to sort of categorize these various types. So one really nice example is tax returns, all right? So what do you see in tax returns? You can either use software like TurboTax, you could hire a tax prep expert, or you could hire a financial consultant and work with them to optimize your tax returns. So there's an example of self-service. Provider-led interaction, you basically dump your files at your tax preparer and say, please help me, or collaboration with a financial expert. And these three are sort of part of a triangle, which you will see depends on the ability and willingness of customers to participate in the co-production process and the diversity of needs by the customers, or in your case, the patients. So just as an example, if there's a fairly low diversity of needs, then self-service makes a whole lot of sense. But on the other hand, if there's a high diversity, you need true collaboration. And again, bringing it back to your world, you have a very high diversity of needs from your patients. And typically, then you will have collaborative services where you're working with your patients to figure out what's the right treatment over time. So just as another example, and then I'll just finish up because we only have a minute left. A very good example of self-service might be diabetes management. At this point, diabetes management is a fairly well evidence-based field, and we can set it up as a self-service. Orthopedic surgery, just doing the surgery is provider-led. You don't have patients operating on their own knees and hips. But knees and hips, as I learned last night, is pretty straightforward. You know what you need to do. Any orthopedic surgeons in the room? Okay, I can say any. Oh my God, all right, I can't say anything I want. But in general, it's a fairly straightforward thing. But I'm gonna correct that in a second. There's one thing there. And then finally, chronic care is a very important area where you need a lot of collaboration and a lot of work between providers and patients. I should say, though, back to orthopedic surgery, you guys, there is a lot of collaboration in things like pre-surgical decision making. What is the right treatment? Is it good to have surgery now? Should we wait? That shared decision making is a collaborative process. And there's certainly collaboration in post-surgical care. There's a lot of patient involvement to make sure that works well as well. So you can see, again, all three types of co-production within the healthcare space. So just to summarize, and then I can let you guys go, variability in systems, that's been the theme of this talk, can lead to lots of things. Delays in in-process waste, the need for capacity buffers, extra capacity to handle that variability. And the larger the variability, the larger the capacity buffer you need. Resource pooling is a way of managing that variability. Information sharing is another way. And finally, the need to select the right co-production design, given the variability in the patient needs and the ability to participate in the process. So that's it. Bob, did I get the whole course in an hour?
Yes, I don't remember anything.
I didn't cover. Great. Okay, thank you. Actually, there's a whole part on Lean and Six Sigma that we covered as well that we can get to some other time. I guess, if you can stick around, I'm happy to talk and answer questions, but thank you for your participation in that, and I enjoyed it. Thanks. Thanks. Questions, comments? Yes?
Just in terms of the queuing, at airports you have TSA clear and other lines for priority. So should we have a TSA pre for the ED?
Yes. Yeah. The question: should we have a clear or sort of a fast track for the ED? Certainly, there are ways in EDs. Fast tracks are one method to help patients get through the system faster if their needs are lower. And there's always actually in queuing. This is the pushback against pooling. If you can separate patients who have clearly different sets of needs, and especially if you can separate patients into high variability and low variability, where patients who are coming in with much less significant needs, you will help yourself by moving them into a separate track. So in a high volume ED, yes, having a fast track for low acuity patients can help a lot. Of course, having a fast track for patients who can afford it is a different ethical and moral question. But certainly, if you can separate out those with different needs, that's important. Great point. Thanks. Other questions, comments? Yes.
What are your thoughts on lean processes in healthcare? Because lean processes in manufacturing work. But in healthcare, we're not really manufacturing things. These are patients and human beings.
Yes.
So what are your thoughts on the application of lean processes in the clinical and in the surgical world?
Perfect. Beautiful question. Thank you. So the question is how appropriate is it to take methods that were developed for manufacturing, like Lean or Six Sigma or Toyota Production System or all these other buzzwords that you hear, and apply them to healthcare? Now, I'm a believer, but I'm a believer with a caveat, and that is understanding that yes, we're not building cars, we're treating people, and you always have to keep that in mind. And this is a bit of a cliche in the lean world, but the whole idea of lean in healthcare is to standardize and automate and lean the things that are most appropriate, the things that can be standardized, the things that are common to all surgeries. And you already do this perfectly naturally. When you guys have a tray, I suspect that when you have a tray with indents that are the same shape as the tools that go on the tray, that's a classic example of lean. Okay, that's making problems visible before they happen. You have done that for decades. You have created standardizations where it's appropriate, and then that frees up time for the things that vary among patients that cannot be standardized. I think the debate in lean is where is the boundary between the common processes that can be standardized and the not so common processes that we're going to leave to individuals to sort of create as they go along and to customize for patients. So therefore, I think it's a question of degree rather than if. Everything could benefit from some lean examination, but to what degree, I think, is where you see disagreement. So I spent yesterday at Virginia Mason. As you probably know, they are fanatical about pushing that boundary as far as possible. Other hospitals have pushed back. But I think every hospital, whether they know it or not, is doing some standardization and some sense of lean improvement. Does that answer your question?
Yeah, but does that correlate to patient satisfaction?
Patient satisfaction. Bob and I were talking about patient satisfaction earlier. So to what extent is patient satisfaction a good measure of outcomes? Okay, so we actually, I can go down a list of pros and cons of patient satisfaction. First of all, I am not a big fan of patient satisfaction as a measure used for quality improvement. It's very hard to connect happy patients or satisfied patients with actual better care. All right, the connection between those is very, very loose. So when your scores go up or scores go down, does that tell you what you need to change? You don't know. It's hard to connect the two. I think it's better to get very specific patient satisfaction scores on specific parts of the process, but even there's trouble. So I'm actually looking at research right now that looks at, did the doctor help me manage my pain? That's a very common satisfaction. Well, what's one easy way to manage pain? Meds, what kind of meds? Opiates, okay? So there's evidence now that the implementation of patient satisfaction scores in hospitals like that one increased opioid prescriptions, all right? So again, what's the goal here? The goal may not be a happy patient in the short run, all right? So we have to be really careful what the goal is. And I think one part of lean is to think about, well, what performance measure is most appropriate for assessing quality in the system and finding those best performance measures. So great question. Yes?
One other thing, I think, everyone gets caught up on all these measures and everything. It's interesting, even when you discuss, everyone wants to make healthcare like as if you're producing a car or like it's like a production, right?
Well, I disagree with the premise, Rod. I don't think anyone, most people don't want to do that. I think what most people want to do who do this kind of work is make healthcare more personal and more a better environment for both patients and providers. And the idea isn't to turn people into cars. The idea is to create a process that doesn't put everyone in impossible situations, like the situations we saw earlier, okay? So there's nothing good about a stack of patients sitting there waiting for you, okay? These are not happy patients. You are not, actually, you look pretty happy, actually, Rod, kind of happily drawing these beautiful pictures. But I'm afraid, and this is the point, and I'm gonna pick on Rod because he was actually, I didn't get to come back to you. Rod was here at the end of the line doing his own thing in a beautiful way, okay? This is absolutely fantastic. And these may be the happiest patients in the world. But I think the essence of some of this is to say that you are not an island, okay? What you do, you may think you're making happy patients, but the implications for the rest of the system are enormous. You have 9 people here who are working away and an enormous bottleneck at the end, and incredible domino effects on the rest of the system. So we're trying to ask people to expand their view and think, you know what? I know this is good, I think this is good for me and my patients, but let's work with the system as a whole to make sure that it's working for everybody. And I'm not having these exogenous, these slipover effects from what I'm doing. And understanding that is what we're after. Does that make sense, Rod?
Yeah, it does, but what my point is that I think, for example, in healthcare, for me, is, there's such little emphasis on like making the provider happy and supporting the provider and like their mental health, their well-being, what's their office like? Do they have the support staff? Because I think, again, I sort of, just being in a larger quote-unquote system that's always trying to get more efficient, that's one of the, like things you can't put a measure on. But if you have a happy doctor versus someone that's upset, and I think when you work in larger systems, they have a hard time, like, that gets kind of lost in translation.
Absolutely. No, I mean, there's in any service, and the best service companies understand that the satisfaction of frontline providers, has an enormous effect on the reactions of customers. So if you look, Southwest Airline is always held up as an example of one where they're incredibly efficient. They are a relatively low cost, getting less so, but they're a relatively low cost airline. But they also manage to do things with their employees where they generally are satisfied employees. And you can see that immediately. You get on the plane, they're generally smiling, they're a little happy, they're kind of goofy, they're having fun, and this is good. This is good for the passengers who fly on the plane. So they found a way to make that happen, but also to get a fairly efficient process as well, which is relatively low cost. So I don't think it's a choice. I think you can find ways to do both, but it is hard, Rod, absolutely. I agree, that's an important point. Other comments? Great questions, comments. Thank you. You guys got work to do, and keep at it. Thanks. Thanks.